Cool, awesome. So thank you so much for coming today. I'm very glad so many of you made it to the iCampus today. And I'm very happy to have Vinny from our company, Merantix Momentum, speak today on accelerating physical simulations with graph neural networks. But before introducing him a little bit, I'd like to say a word or two about our company, what we do, and why we're here. So we are Merantix Momentum. We mainly do two things. So we have a consultancy business in machine learning. So small to medium-sized enterprises come to us, and we assist them in implementing machine learning solutions for their specific use case, and assist them in going the whole life cycle from like what is the problem to implementing a solution and maintaining models that we trained. And the second thing we do is research. So we have a research division that's slowly growing over the last months now, and we're very proud of that. And that also brings me now to Winnie, who is one member of our research team. And he is going to talk a little bit about graph neural networks and what they can do in the simulation domain. And Vinny has published a paper on this at a workshop at ICML last year. And I think he will take you on a little bit of a journey where he, or like what graph neural networks do, and how he came then towards his publication. And we're very excited to have him here today. And yeah, as I said, please drop any questions in the chat, or just interrupt, raise your hand, and then I'll pass you the mic such that our online audience can also hear what you're saying. Awesome. Then take it away, Winnie. Thank you.
Thank you so much. Thanks a lot, and thanks everyone for coming. Warm welcome from my side. Like Alex said, I'm a machine learning researcher at Merantix Momentum. I joined at the end of 2021, and I'm very excited to tell you a little bit about our work about graph neural networks and physics simulations. And like Alex said, feel free to interrupt at any time. I'm also taking questions at the end, but if you have something, just raise your hand. We pass the mic around. And to start off, I just want to motivate a little bit why it makes sense to look at the specific kind of physics simulation I'll be talking about. I'll be talking about simulations that solve PDEs, or partial differential equations. And for those of you who haven't heard the term before, a PDE is basically the case where you are looking for a certain function, and then you have some equations that contain derivatives of this function. And then from these equations, you try to compute, or you try to find a solution, which means you are looking for this function. You're trying to find this function that is described via its derivatives. And this is a very powerful formulation because you can find it everywhere. You can find it in all kind of natural science disciplines. For example, it's heavily used in weather forecasting. It's used in aerospace industries, for airflow prediction, for fluid dynamics. And it's also used in engineering disciplines. For example, we at Merantix Momentum, we have a research project where we work with a automobile manufacturer, and we try to find the magnetic field in electric engines, and you can also do that with PDEs. So it's quite an interesting topic that we'll be talking about. And just to give you a little bit of a understanding how such a PDE looks like, we will start with a very simple equation, a very simple example at the beginning, which is the Poisson's equation. The Poisson's equation can be used to describe how an electric charge creates an electric potential in some space. So this is one example of the Poisson's equation. There are many more, but I will focus on this one example to give you like a very crisp idea of what this equation does. And I will try to work you through with this example through the methods later on. So if you look at this equation here, this is basically the sum of the second derivatives of this function u along the spatial dimensions. So we derive 2 times, and then we say that the sum of these derivatives should equal the fraction here. And what this u basically means, it's electric potential, and the rho parameter here is the electric charge, which basically tells me where or the electric charge distribution, which tells me where my charge is located in the space. And this epsilon here is a material constant that basically says what is the resistance of the material towards building up an electric field. So that also has an influence. And with this equation, I can describe a process that looks like this. So I have an electric charge here. I think all of you will kind of have an intuition about what an electric charge is. So when I, rub something, then I create some, charge. And around this, the space around it's basically, we basically create an electric potential, and it looks like this. And this formula helps us to describe how the electric potential spins up in this space. Oops. And if I write it down in the 2D case, like we can see here, I can write out that formula. I have the second derivative with respect to the x dimension. I have the second derivative with respect to the y dimension of our function u, which describes the electric potential, and it equals at every point. And now I have moved this negative sign to the right side. It equals the electric charge distribution at this point divided by our material constant. So that's the formula, and now we have to solve it to get our electric potential, which we want to compute. And if we simplify this a little bit further, and we just assume that our electric charge distribution divided by our material constant is 1 everywhere. So let's assume we have like a constant charge that is distributed over the whole space, and our material is also the same everywhere. Then we can replace this term on the right just by a constant. And this makes the equation even a little bit more simple. And I will use this example throughout the talk to kind of motivate the different neural methods later on, and to show how they learn on this kind of PDEs. So what we have here now is a very simple equation that says the second derivative of the function in the x direction and the second derivative with respect to y, when I sum them up, I want to get -1. And now I know intuitively how the electric potential changes in my space. But there's one more information which is missing, because basically with this formulation, I have an infinite amount of solutions, because if I only know how it changes, I can add basically a constant to my electric potential, and it still satisfies this equation. So I need to know at some point in my space, like, what is the exact value of the electric potential? I need to fix it. And this is what's usually called a boundary condition. So we also need that. So we need to say at some point, x, y in my space, I have a fixed value for my potential. And then I know once I have this like boundary condition, I know I can exactly compute the potential in my whole space. And let's say we look at the circular domain, the unit circle in this case, and we set the value of our electric potential to 0, then we get something like this. So we can write down the solution of our PDE in a closed form of this equation. And the solution looks like the formula I plotted it on the right here. So this is a rare case. Usually it's for these types of equations, it's really hard, or it's almost every time impossible to write the solution down in a closed form. And I will elaborate a little bit more on that later. But in this very simple case, in this very simple example, it's possible to write it down like this. And that's why I will be using it throughout the talk to showcase some of the examples later on. And yeah, if you intuitively think about it, it makes a lot of sense, because you basically have an equal amount of charge distributed over the whole space, and then you also know that the electric potential on the boundary, like at the very at the boundary of this unit circle, should be 0. And then of course, like the electric potential is going to be very high in the center of the circle, and it's going to decline when you move more outwards towards the boundary. And like I said, it's very difficult for general cases to write down the solution, the function that we're looking for in a closed form for these PDEs. And that's why people have invented other things to come up with approximations for these functions. So here I have plotted a solution for a different type, or the Poisson's equation with different parameters. And now it's not possible anymore to write it down in a closed form. So if I only have pen and paper, I'm lost basically. So I need to do some kind of numerical approximation. And how it works, I don't have a very deep knowledge about these simulations, so I'm going to just mention the concept very briefly. But it's called the finite element method, this concept. And what it basically does is it computes the solution at a discrete number of points in my space. It discretizes the domain, and then I have a finite set of points where I compute my solution. And if I want to know the solution at a point that lies somewhere between some of these discrete points, I can interpolate. And of course, I'm going to make some errors here. So this is not perfect, but what I can do is I can adjust the size or the resolution of the grid. So if in some cases I'm very much interested in this area here, I can make the resolution of the grid very high. So my solution in this area will become more accurate. And if I say that, for example, in this other area, I don't care so much about the accuracy of my solution, I can make the grid more coarse, and then I can save some compute time, and my simulation will be a bit faster. So this is kind of the trade-off that we can make here. And usually these simulations, they work quite well. And there's obviously something more to it, because—
Excuse me, can I ask you a question?
Of course. Go ahead.
Back to the previous slide. At the finite element methods, can you say that it is exactly equal at the points, or it's still an approximation at the points?
To my understanding, it's still an approximation.
Okay, thank you.
Yeah. But it's of course more accurate at the points than in between. All right, so the rest of the talk, I'm going to talk about neural methods to solve these PDEs. And first of all, I want to motivate a bit, why does it even make sense? Like, now that we have all these great physics solvers, why does it make sense to look at neural networks solving basically the same kind of problem? So the good thing about these FEM solvers is that they can solve a very broad range of PDEs, and they can solve them quite accurately. So many disciplines, like the ones we talked about before, for those disciplines, the FEM solutions, they can achieve necessary or sufficient accuracy. So we can do interesting things. But yeah, like while there is like for various kinds of PDEs, there's like specialized solvers, and they all work very well. The thing is that for each slight change in the parameters of the PDE, so let's say in the example that we talked about before for the Poisson's equation, if we modify the charge distribution just by a tiny little bit, so the solution stays almost the same, but For the FEM simulation, it doesn't matter. I have to discard everything I knew before, and I have to start from scratch and rerun the simulation to get the new result. And this is in some way not the perfect way to do it. And that's why people started to think about neural network approximations, because the idea with these neural network approximations is, of course, that you can learn from this data that you generated with previous simulations. So let's say in our Poisson's equation example, you have simulated two times for two different parameters that are very close to each other, and then you want to simulate a third time also very close to the two other, then maybe your neural network will be able to interpolate between the simulations you ran before, and you don't need to run the FEM method again, right? And also, what we hope is once we specialize these networks to very distinct or very, very specific types of PDEs, they will be a bit faster than the ground truth FEM simulations. And especially they will profit from all the energy and the thought that has been invested in basically making deep learning very fast, because there we have all these nice algorithms that run very efficiently, like matrix multiplication on GPUs, which is still very, very difficult to do for these FEM simulations. So it's not really straightforward to run such a simulation on a GPU, for example, but you can do it easily with a neural network, of course. So I hope I convinced you that it makes sense to look at neural networks that solve such kind of equations. And I want to start with a very intuitive example of how such a network could be constructed. So let's say we want to train a network that solves our PDE. Probably a very intuitive way to do it is to have a network to input our spatial coordinates to tell the network, okay, I'm at this value X and this value Y. Please tell me the value of the electric potential at this point, right? And then if you want your solution over the whole domain, you just put in different values for X and Y, and then you get everything you want out of the network. So that makes a lot of sense. It's very intuitive. And this kind of network, it has been introduced by the paper I mentioned below. It's called a physics-informed neural network in the literature. And in the next step, I'm going to show you how this kind of network is trained. So basically, it is trained also in a very straightforward way. We just take the PDE and we learn from the PDE directly. So if we think about this example that we mentioned before, there we said that the sum of our second derivatives, the sum of the second derivative with respect to X and Y, it should be equal to -1. So if we want to construct a loss function for our neural network out of this, we can just say that the sum of these two terms plus 1 should be approximately 0. And we take an absolute value of this and we can directly use it as a loss function. And then if we do this for many steps, if we train long enough, our network will learn to output a function that has exactly or approximately the right second derivatives, exactly what we want. And of course, as we said before, this is not sufficient. We also need to enforce the boundary condition, and we can also do this in a very straightforward way. We just say that all the points that lie on our boundary, that basically lie on the boundary of this unit circle in our small example, they should be 0. Like the network should output values that are close to or approximately 0. And if we use this formulation as it's written down here, we get something like this. So on the right side, you can see the function that the network has learned. So this is basically an animation over the time during training. You have a question? Yeah, you can just use standard MLPs for that, usually. So what you can see is that the network, like if you remember the figure from before, it was very bright in the center, so the value was very high here, and it decreased when you went outwards. So it already looks quite good what the network learns, and what the network sees, like the loss function that the network sees, you can see it here on the left. So this is basically, I plotted the two terms, the two second derivatives, as a vector field. So the x component of this vector field is basically the second derivative in the x direction, and the y component of the vector field is the second derivative of our potential in the y direction. And if you look at this, how it changes over time, you can see that the network really tries to align these arrows or these vectors in a way that they, like, both components sum up to -1, which is exactly what we want. And once this is achieved, you can also see that the solution that we learn on the right side, it looks approximately like the solution that we want to get. So this is very cool. And one advantage of this is that we don't need the FEM simulation anymore. So this works just from the PDE. And it also works, of course, for PDEs where we can't compute closed form solutions. So this is a pretty general and a pretty powerful approach. But it obviously has also a very big downside, which is that we still need to retrain the network for every change in the PDE parameters. So we said before that we want a network that learns to reuse simulations, previous simulations, but that's not what this network does. It's also, it has the same limitation like our FEM simulation, like the ground truth simulation, that we need to rerun it every time. So that motivates us to think a little bit more and to come up maybe with a network architecture that doesn't have this limitation. So how could such a network architecture look like? What we definitely need is we need to tell the network our boundary conditions and our PDE parameters, right? So we want to solve not only a single instance of our PDE with given parameters and boundary conditions, but we want to solve a more general case. We want the network to be able to predict, to make reasonable predictions for different kinds of parameters and boundary conditions. So we need to give these things to the network as input. So this input, the first one, basically tells us where are the charges located in my domain. And the second input tells me where is the boundary of my domain. So the network needs to know this because, as we said before, the potential at the domain is set to 0. And with this information, the network should be able to predict the electric potential. So now there's two basic problems with this architecture for a neural network. The first problem is, how do we train it? Because before, training was straightforward. We could just use the PDE for training, but now we need a more elaborate approach. And what people usually do is they use ground truth FEM simulations to generate data, and then they train this network with the data from the simulation. So you still need to run the FEM simulation to a certain extent, but of course you hope that once the network is trained with the data you generated from the simulation, then that you don't need the simulation anymore if some new PDE parameters arise. And the second problem that is closely related to the first one is that now our training task is much more complicated. So before, we just wanted to learn the solution for a single PDE, which is straightforward, and it can be done with simple MLPs in most cases. But in this case, we want to learn a general solution for very different kind of parameters and boundary conditions. So this is a much more complicated problem that we are trying to solve here. So we also need a more powerful network architecture. And one network architecture that works very well in this kind of cases are graph neural networks, as you might have guessed from the title. And why do graph neural networks work well in this case? So if you remember before, we said that these FEM simulations, they work on discretized grids. So they compute the simulation at discrete points on our domain, the solution on these discrete points. And like we said, it is very much possible, and also it makes sense to have different resolutions for this grid in different areas, like areas where we could care more for accuracy, we should have a higher resolution. And this kind of data, like learning on arbitrary grids, but I can directly do that with graph neural networks, because graph neural networks are a very general concept. I just have nodes and edges between those nodes, and I can learn from any kind of data that fits into this framework. So graph neural networks are a natural choice for this type of data. And just for those of you who are maybe not too familiar with how such a graph neural network works, I have 3 slides to explain the general concept. So graph neural networks are organized in multiple layers, and each of these layers allows neighboring nodes to send messages to each other. So this concept is called message passing in graph neural networks. So what happens here is that, for example, if you look at the node here, it receives messages from all of its neighbors, and then these messages or these bits of information are aggregated with a function, and then another learnable function, like a function with learnable parameters, is applied to this aggregated value to then compute the new state for this node. And this process is basically repeated for every node in the graph. And then you have a set of new states or values for your nodes. And if you do this over and over again, you can also distribute the information over the whole graph and not just between neighbors. And that's exactly what a graph network does. So it adds more of these layers of message passing. It repeats the message passing step multiple times. And then you can also, like, basically you can send messages from different kind of from nodes that are also like a few hops away from each other, depending of course on how many of these layers you have. And if you write this down in a mathematical formulation, it looks like this. There are different formulas for how the aggregation and how the node values can be computed, but this is a very general and a very simple one. The GCN formulation, which was introduced by the Max Welling group. And what it basically does is it computes the mean over all the neighboring feature vectors it computes the mean of the feature vectors of the neighboring nodes. And then it multiplies this mean with some learnable weight vector. And it also multiplies the previous feature vector of my current node with some learnable weight vector. Then all of this is passed through an activation function. And in the end, I have the new feature vector for my current node. And this process is repeated for all of the nodes. And then I can do this multiple times to have many layers in my graph network. And if I want to apply this type of architecture to PDEs now that we understand a little bit how a graph network functions, I just want to like briefly summarize the process again. So as we said, we generate ground truth data with our FEM solver, with our physics simulation. Then we have these solutions and we create a data set from them. And then we use this data set to train our GNN operator, our neural network. And what has been very effective in practice is to build the operator not only using a GNN, but also at a encoder and a decoder before and after the GNN basically. And for those, you can typically also use just MLPs. So the values or the feature vectors are pre-processed before you feed them into the GNN, then the messages are sent around on the graph, and afterwards you can have a little bit of post-processing on your feature vectors before you read out the interesting information. And this concept was like one of the first papers that used this concept was this DeepMind paper that I mentioned here from Tobias Pfaff and co-authors. And people have rapidly adopted this structure afterwards.
Vinny, we have one question from the chat. So apparently mesh generation seems to be very computationally intensive in traditional FEM methods. Do the graph neural networks expect the mesh generation to be already done, and or do they assist you in a way to generate a mesh as well?
In this case, the mesh needs to be created before I feed the data into the graph neural network. So that's true. If you do like the triangulation, like whatever triangulation you use, Delaunay, etc., you need to do it before you feed the data into the GNN. It expects the structure to be already there.
Doesn't that limit the scope a lot? Like if you have to like know the mesh beforehand, essentially?
I mean, the mesh can be different for different samples. So I can have the same GNN network, and this is, I think this is exactly the power of the GNN architecture, that I can run the same network for different meshes. I need to know the mesh, but it doesn't have to be the same for all of the samples.
Okay, got it.
But it's true that, I mean, there's some computation over it. I think,
yeah.
Okay.
Listen,
You'll be next.
other question, what comes a little about your narrative in a way. So you say that, okay, it's easier to actually do the pin system, the physically informed neural networks, if you would actually train this kind of a function out of it, and because then you only have a pointwise system in your hands. So why do you say that you are using FEM for them, for this in this kind of a, because why wouldn't you use a pin to actually produce the solutions that you're actually using here, in all of those cases?
You mean
that would be more efficient than
if I understand
you have parallelized? Yes.
Yeah, thanks for the question. So I think it's a very good question. If I understand you correctly, you are asking why we just can't use the pin loss for the second network to train it as well.
Or actually for your training solutions.
Okay, makes sense. So
because you have a FEM there, and then you say that actually the pin is better for that.
The reason why we want this more complex architecture, the neural operator, which can deal with. Okay.
Where do you get your training data?
Okay. So you mean you can use a pin to generate the training data and then train an operator on top of that. Yeah, that would work. I think there are people who have also used the pin loss directly to train an operator. That should also work to a certain extent. But it's just easier if you get the ground truth data from the FEM simulation, or you can even do both. You can have some ground truth data from your FEM simulation, and you can have the pin loss on top of that. So there are also people who do that. I think it's just a matter of like what works in the end for you, and it's easier, like you get results faster if you start from at least some ground truth samples from an FEM simulation. And you know that those are accurate because you know the simulation, they have like provable guarantees and this kind of things. But it's more like I think you're completely right. There are many ways to do it. It's just a matter of like what people have done in the past, and usually they use these FEM simulations to generate the data, but there's many other ways, I would say.
See that the narrative goes so that it's better way of doing it with pins rather than with FEM, and then you say that, okay, I really trust the FEM more with my training.
Yeah, I think there's reasons to trust it more, maybe. Okay, I think John, you had a question.
I was wondering, like in your example, to frame this example, if you can think of your original slide where you showed an airplane wing, and you said like maybe at the front of the airplane wing we'd want a higher resolution mesh to calculate our PDE. In your graph neural net, if you have nodes at a higher resolution, is there some way that you indicate that to your graph kernel, saying like, oh, the edge weight between them is smaller, or they're connected to neighbors that are further away?
Yeah, that's a very good point. I'm going to come back to that a little bit later in a way, but in general, I would say usually you don't have that in classical graph networks, and it's a problem. So what you would need to do is, so basically the graph where you carry out your computations, it doesn't have to be the same like the graph that the FEM simulation uses.
Okay.
So of course, like you can introduce additional connections into your graph, or you can, let's say, use a different operator that spans multiple hops. But you need to invest some thought into that, how to do it properly. And I think that's an active area of research, I would say, like how to kind of rewire the graphs such that information is passed most efficiently. So for example, if you have a very dense area where you would like to introduce some like skip connections between more distant nodes to get the information where it should be. But then of course, like it's a bit tricky, like how to find out where to add these edges in the best case.
Cool. Thank you very much.
Kind of a follow-up. In practice, can you use this on like a course resolution and then use those as initializations to then do a more granular resolution, like with the airplane wing or something, to like accelerate the process? Or if you initialize it with a course thing, you're better off just starting from scratch? And also, what about like other invariant quantities like energy conservation or like incompressibility, this sort of thing? Like, does this come out in solving the PDE with these losses, or do you have to incorporate those in the losses as well?
There have been prior works that showed you can generalize to a certain extent across resolutions. So factor 10 should be possible, like for some cases, and maybe more if you design your architecture in a clever way. And I will heavily cover generalization in the second part of the talk, because that's what the paper is about. But about the physical constraints, you would have to manually add them to make the network learn it.
You look at like adjacent points and you say have like an incompressibility constraint, like you might be fitting the MSE function, but it would like violate some physics or something.
Yeah, I think like my very basic knowledge of physics. So my understanding is that this PDE describes the process exactly. So if you fit the PDE, you should not have any physical implausibilities, so to speak. But of course, it's an approximation, and these things can happen. And then it might help the network if you introduce an additional loss. That would be my guess. All right.
We have one more comment from the online community, which says that using the pin loss to start off with is usually very complicated because it's much more nonlinear. It's usually like common practice to first start with FEM data and then switch to the pin loss later on.
That makes a lot of sense. Yeah, so very good comment. Thanks.
Thank you.
All right, where were we? So I just wanted to show you the learning of the neural operator again for the simple example that we talked about before. And now, if we assume that we are doing it the very classic way, just generate some examples with our ground truth FEM simulation, and then we learn from that. We can use a very simple loss to train our operator. Now that we have ground truth data, for example, just a mean squared loss, like or squared loss in this case, and just compare the data or the output of our neural network with our ground truth, and we're good to go. And we don't even need to add the boundary conditions separately here because they're already included in the ground truth outputs. So that works nicely. And just for the sake of completeness, I have also included a little visualization how it looks like. So here I trained the graph neural network on this only one data point, the one that we talked about before in our simple example. And you can see that this is what the network sees. It sees the MSE. It's not very surprising that it really quickly learns the correct solution. And as I think Alex, I don't know who posted it in the chat, mentioned correctly, it converges much faster than the pin loss. So if you have ground truth data, it's easier for the network to learn. And that's, I think that's the main reason why people are doing it this way. Now let's summarize what we learned about the neural operators. They have also certain advantages and disadvantages. So the main disadvantage, of course, is that in our current formulation, like what we are doing right now, or how we talked about it, we need ground truth training data from our FEM simulation. So we are not able to completely discard the simulation, but in theory, or what we hope for is that we can solve a whole class of PDEs with all kinds of different parameters and boundary conditions. And we would like to do that without retraining. So we would like to be able to generate a data set with our FEM simulation, train our network on this data. Hello? And then be able to generalize to unseen PDE parameters and boundary conditions afterwards. And that would be very good or very helpful, because then, for example, we can generate, let's say, 10,000 samples with our FEM simulation, but our neural network can maybe solve 100,000 or 1,000,000 problems. And this would be really helpful for us, given that the neural network is faster than the FEM simulation. But we need the network to generalize. And we already talked about this a little bit. And this is also what our paper was about last year. And this is joint work with Simon and Johannes. We published this paper at the second AI for Science workshop at ICML. And it's basically exactly about this problem. Like, how do we ensure that this graph neural network generalizes as well? And we are looking at two types of PDEs, which are basically just variants of the Poisson's equation that we just saw. So the first type of PDE we're looking at is very simple, the electrostatic simulations that we already talked about. Our simple example, basically, in a little bit more general case, like now we have flexible charge distribution, so we can have charges everywhere in our domain, and we want to know what is the electric potential. And then the network should also predict the electric field, which is basically just the gradient of the electric potential. And in a similar sense, we can look at magnetostatic simulations, which are also governed by Poisson's equation, and we can look at electric currents that basically produce a magnetic field, and then we can task the network to predict a magnetic vector potential and magnetic vector field, which is basically the rotation of the magnetic vector potential. And now, like I said, what we really want to do, like now that we have these specific instances of PDEs that we are testing with, we want to construct a task that allows us to see if the network generalizes as well. And there are two things that basically we had on the top of our mind, how we could possibly do this. And the first thing, I think we talked about this a little bit already, is generalization across shapes or different types of meshes. So let's say in this example, we train on 4 different types of meshes. We train on a circular domain, on a square domain, and we also train on a domain that has a little hole, and a circular domain with a hole, and then also a square domain with some kind of cutout. And we want the network to make reasonable predictions for a domain that looks very differently, for example, like a U. And you need to understand that this is like a very different scenario, because what we said is that on the boundary of the domain, the potential always needs to be 0. So this boundary looks very much different than the boundaries here. And if the network makes reasonable predictions for this other boundary, it will be a very good thing. And it's actually a bit tricky to get it to do that. And the second thing we looked at is superpositions, which basically means that in our training set, we have a limited number of charges or currents. And in our test set, we have more charges and currents. So for example, you could imagine that in our charge distribution, we have a charge here in our training set, and we have another charge in some other place. And in our test set, we have both of these charges in the same sample. So the network needs to deal with a more difficult charge distribution here. And we ran the network, or we trained the graph network just the way I introduced it before, and it didn't work very well. So we were thinking, how can we improve the generalization of this thing? And one idea that we had is, when we wanted to generalize better, we should increase the variation in the training data. So what we did is we went back to our ground truth simulator and we varied the grids a little bit for running our simulations. So for the disk with the hole, we varied the size and the location of the hole. For the square with the cutout or the L mesh, we controlled the size of the cutout and the location of it. And for the disk and the square, we varied the node density. So basically, we ran exactly the same number of simulations, but on more different grids. And we try to find out if that helps us, if that helps the network to generalize better. And we constructed 4 different data sets with this process. So the technique that I described before, like varying the grids a little bit during the run of the FEM simulation, this is what we call mesh augmentation. And we have basically 2 training sets. One training set without mesh augmentation as basically to check like what would be the result that we get out of this. And then when we have second training data set where we apply mesh augmentation, and those data sets have exactly the same amount of samples. And they also have the same amount of charges or currents, and they have the same shapes like the circle, the square, the L, and the circle with the cutout. And then we have 2 test data sets. One test data set to test for shape generalization, which contains only this U-shaped mesh and also between 1 and 3 charges or currents. And then we have another test data set to test for superpositions. And this one has the same shapes like our 2 training data sets, but it also has more currents or charges than the network has ever seen before. And now what we do is we basically train the network 2 times on the training set with mesh augmentation and on the training data set without. And then we check the test performance on the 2 test sets. And what we get out of this is quite impressive. So for the shape generalization, the test loss really goes down by a lot. You can barely see the green bar here. And what I especially found most interesting is that also for the superposition test set, the test loss goes down by quite a bit. And this is not really intuitive when you first think about it, because our mesh augmentation, of course, like it augments the shape, so it definitely helps for the task of generalization across shapes, but it also helps for generalization with different numbers of charges or currents. I wasn't so sure about that, and it actually worked. So that was a bit surprising and a nice result, in my opinion. And what we also did is we looked at other techniques to augment graphs. So what people do sometimes in the literature, they just randomly drop edges from the graph, like you can see in the image on the left with a certain percentage, or they randomly drop all the edges that are connected to a certain node, which is referred to as node dropout. Or what they also sometimes do is drop out some elements in your feature vectors and try to improve the variance of the training set like that. And we do a little comparison where we show that our proposed mesh augmentation is better than all of these techniques, but also we can see, and this is again the results for the shape generalization test set, that both node dropout and edge dropout also help the network to generalize to a certain degree. And now I think there was a question in the chat.
Yeah, I'm currently reading it. A very general question. It seems to me that all the work done for generalization could have been done for a uniform mesh and CNN instead of a non-uniform mesh plus GNN. Is that the case, or GNN plays a very important role here?
So the question is about whether to use CNN instead of the GNN. Can you read again?
What the difference is between using a uniform mesh and a CNN and a non-uniform mesh and a GNN?
Right. Okay. I think I get it. That's true. If we have a uniform mesh, we can use GNNs, and there are papers that do this, and it works. But like I said, it makes sense to use non-uniform meshes. So at some point, it really has an advantage to use GNNs. In this case, the meshes were not really non-uniform. So we could have used GNNs in that case, but we wanted to see, it's just more like we want to see if we can get it done with graph neural networks, because we know that they have certain advantages. For example, if you have simulations that require you to have a different node density in certain areas. And we know that for the problem that we want to solve in the end in our project, which is the simulation of these electric engines, we have exactly this case. So for the electric engines, you have to imagine that there's basically a static part, the outside of the motor, and then there's a rotating part in the middle. And basically, the only area that you really care about is the very thin air that is between the rotating and the static part. And there you need a super high resolution of your grid. And everywhere else, you can have a very coarse resolution because it's not really important to information. And if you want to apply a CNN to such a problem, I think it wouldn't work very well. So that's why we chose to go with graph networks in the first place. But I think in this very constructed example, you would get good results with CNN. So I agree. And let's maybe, for the last slide about this paper, look at the runtime comparison. So I promised you before that the neural network would be faster than the FEM simulation. So I just wanted to prove it to you guys that this is actually the case. And we used the Phoenix FEM simulation library. So I'm pretty sure you could find another library that works a little bit better or is maybe a little bit faster, but this is the results that we got. And it usually only runs on a CPU. We had 16 CPU cores, and the blue line is basically for different graphs with different numbers of nodes, the time that you take to run the simulation for one sample. And yeah, like I said, the blue line is the ground truth FEM simulation. The red line is our graph neural network on the same number of CPUs, and the green line is our graph neural network on a small GPU, the Tesla T4. And you can see, like, note that this plot is in log space, that our graph neural network is at least one order of magnitude faster, or even a bit more if we run it on the GPU than the ground truth FEM simulation.
The performance hit on your GPU from like 10 squared to 10 cubed, like you're flat instead of kind of going down linear?
I guess that's because when you have a graph that is smaller than this amount of nodes, it doesn't use all the parallel compute units of the CPU of the GPU. I guess that would be my assumption.
Either way, it's way faster. I'm just curious how it's
No, for sure. I mean, I think if you like have multiple samples and you ramp up the batch size, you would actually see it would disappear. That would be my guess. Yeah. All right, and we are almost at the end of the presentation, but I don't want to let you go like this. I want to give you a few bits and pieces to think about maybe, and mention some future directions of research that I personally find interesting. And I'm sure like it has been a very exciting discussion with you guys already, and you mentioned very different ideas, and I will definitely take them away and ponder about it a bit more. But I have also brought you some of my ideas, or what I think that could be relevant to take this idea to the next level. And one of the problems, or one of the challenges that we are facing when we go from this like very simple examples to real world use cases, is that we have to deal with very high resolutions. So if we think about this simulation of the electric engine and about the very densely sampled area between the static and the rotating part of the motor, it might not be sufficient to have a fixed number of graph neural network layers to propagate the information over the whole graph. So if we have like very many nodes, the information just gets lost in the graph because no matter how many graph layers we add, it's just not enough, right? So if we have two nodes that are, let's say, 1,000 hops apart from each other, then it's super expensive to add 1,000 graph neural network layers. And that might not even be enough to get the information where I wanted, to distribute it over the whole graph, which might be necessary in some cases. So what we need to think about is, like I briefly mentioned before, the graph that we use for computation or for running our graph neural network, it doesn't have to be the same graph that our FEM simulation uses. So we are, of course, we are allowed to add or remove edges as we like, and we should do this, but we should do it in a clever way such that the information is distributed most effectively over the graph. And one paper that I found quite interesting, they do something like that. So they basically have a radius, and within that radius, they connect all the nodes in the graph. So every pair of nodes that has a distance below this radius is connected. And then they go basically to the next stage, and they randomly subsample some of these nodes. So in this specific case, they subsample from 400 nodes to 100, and then they also increase the radius. So for these like randomly subsampled nodes, they will be connected even if they have a larger distance. And then they do this again, like they subsample the number of nodes again, and they also increase the radius again. So in the end, you will have very few nodes, but a very high radius. And those nodes can basically pass information over the whole graph. And then the hope is, of course, that by doing this, you get like kind of, like highways on your graph where you can pass your information along. And then the like smaller connections would again like distribute the information locally. And this seemed to work quite well, but of course it's also not optimal because it really depends on your random selection of nodes. So sometimes you might select some nodes that are not really optimal. So I think that's a very interesting thing to think about. How do I select the nodes where I want to build these like long-ranging connections? And I don't have a definite answer to it. It's for sure an interesting problem to think about. And the second problem that I want to mention is physical plausibility. So sometimes when you run the model on some data, or when you look at the worst predictions of the model, you can see that it clearly violates some physical constraints. So for example, in this case, I observed that the electric field that is predicted actually has some kind of rotation. So you can see here, this is the direction of the electric field, and the color is basically the strength of the predicted field. And you can see that somehow the network predicts this rotating field in this place here. But we know from the Maxwell equations that at least in the static case, like if we don't have a time dimension, the electric field doesn't have a rotation. So that's a bit like, you don't need to understand the physics, I think, but even like, yeah, I also don't understand it, but I know that this equation exists and my network shouldn't do this. So the question is, can I somehow add another loss term that forces the network to be physically plausible? And the second question, like related one, would be, does it help me for getting a better test performance? So that would be very interesting, I think, and it's something that would maybe be even a low-hanging fruit, like just trying to add some of these loss terms and see how the performance changes. And the last thing, of course, that is also like super interesting and super relevant is, how does the network behave if I run it or if I train it on different types of PDEs? So for example, I trained this same network that I just talked about on linear elasticity equations, and it horribly failed. Like it did predict good results if it stayed within the same shape, but I couldn't get it to generalize across shapes. So this is also like very interesting for me to find out why does it not work for a certain kind of PDEs, or it works for other kind of PDEs? And how can we ultimately like build a network architecture that is robust against these changes? And in the best case, you can have one network architecture that you can use with different kind of PDEs, or at least you get some kind of recipe that tells you if you have this type of PDE, you should use this type of architecture or something like that.
Were all your experiments done on like a steady state solution? So like if you had a time component, does this become exponentially harder? And also would the time component maybe help it to generalize? It has to learn, because I know like even in other areas of ML, like doing this sort of like masked auto encoding and stuff, where it's like filling in the gaps. You could like, the analogy would be like, this is like filling in the time and maybe like could generalize more or something. Yeah, like have you done like transient stuff or do you think that could help? I don't know.
That's an excellent question. First things first, I haven't done any experiments on time-dependent PDEs, so that would also be next step. But there are, of course, like many papers that look at this time-dependent equations, and what you can do is, of course, you can just use the time as another dimension in your space. So you can use these methods that we talked about to solve time-dependent PDEs if you just add a third dimension, which would be the time in your space. But it depends, it really depends on your problem. If you have like a very long time horizon, this might not be the best way to do it. And that's why people also use autoregressive methods to solve these time-dependent PDEs. And then you basically, you know, you have to do a certain number of rollouts of your network to get the solution like in a certain amount of time steps. But I haven't done it. Right.
There's one more question in the chat. Nima is asking if you have a comment about why it works for some PDEs and not for others. PDEs are strongly different in their nature. It might be a good idea to have a look at different types of PDEs, elliptic, parabolic, etc.
Yeah, I would agree. Also, I think my knowledge of these different types of PDEs is very limited, so I'm not trying to speculate here why it doesn't work, but it's certainly related to the type of equation, why it doesn't work. Then I have only one slide, and thanks so much for staying with me through this presentation. And I just want to summarize the main ideas that I tried to get across in this talk. So first of all, I think PDEs are very interesting problems to look at, and they have a very wide range of applications. And I think also that neural network approximations are a very effective tools to speed up PDE solving, and that they compare nicely to numerical solvers. When you look at certain properties, for example, they can reuse previous simulations and the like. Also within the neural PDE solvers, I find the neural operators that we talked about in the second half of the talk very powerful. And one of the main issues or one of the main challenges is to help them generalize well across different axes. And then there's also some research questions that are still open in my opinion, and where it would be very interesting to look into them, like of course, like what are other augmentation techniques that we could try? How can we generalize to very different resolutions? How can we incorporate knowledge from physics? And how can we support multiple PDEs with one operator? And yeah, with that, thank you very much for your attention. And if there are any more questions, I'm very happy to take them now.
One last question.
So there is a good thing that if one is looking at how to solve the differential equations, very often how the pins are doing it or how your system is doing it, it actually learns the ways how the solutions look like. It does not look at the physics anymore, but it has these emergent rules. And this is the same system that, for example, Google used in DeepMind used for solving the Schrödinger equation for folding of proteins. It doesn't look at the Schrödinger equation, it actually look how the proteins are folded, and it finds rules for that. And this is what your generalization is doing as well. So it doesn't actually care about the equation, it's look at how the solutions are going to look like. And that's why if you're actually using the same kind of architecture, sometimes the solutions between different equations are too far apart, or are too different in the sense that the same system doesn't work for them.
Yeah, makes sense. Is there a question, or is it just
Explaining you a little. So.
okay? All right, then I take it from there.
There's one more question in the chat. Have you tried to build the physical constraints into the architecture of the network, such that even an untrained network is fine on the physics side?
That's a very good question. I'm not sure from the top of the head how I would do it, but it sounds very interesting. If you could do it somehow, yeah, sure. I haven't thought about it, to be honest, but it's an interesting idea. I mean, at least you could have certain priors, I guess, that help you, even if it's not like a hard constraint, like how you initialize the network, all these kind of things.
I have a question related to your example of the electrical engine. Is it really relevant for car companies to, like, can you say something about the computational efficiency? Because if I imagine a car company, imagine like a very rich company, and they have like 10 engines or something they want to solve something on, but are they really interested into like solving these equations on millions of engines or so?
I would say yes, because they are in the project, but to maybe make a little bit more of an elaborate argument. So like what we're trying to do on top of this is an optimization. So we have some kind of function that we want to optimize. For example, we want to have the engine with the maximum efficiency or the maximum torque or whatever, like there are certain constraints. And then in this case, of course, you have to run very many of these like predictions from like, you won't get away with just, let's say 100 or 200 samples, but then you have to do like, you know, like 10,000, 20,000, depending on like how your like optimizer is defined. And then like another advantage of having a neural network is that you can differentiate through it. So you have a gradient that tells you how do I need to change my inputs to have a certain effect in my outputs, and that also like of course helps during the optimization. It's like an additional information that I don't have from the classical solver. So it's actually like just saying that it's only about speed. It's part of the story, but it's not the full story.
Thanks.
Thanks for the question.
What software are you using to run this, or how are you doing it in like a technical way, more like a practical way?
Yeah, so the FEM simulation is Phoenix. It's just it's a Python package, and for the neural network I use PyTorch, and yeah, PyTorch geometric.
Okay, thanks.
Thank you.
Oh, if there are no more questions, then I would like to thank you guys so much for coming along. It's been a super interesting evening. Thank you again, Vinny, for giving this amazing talk. And this is not only a space to talk about research, it's also a space to connect. And so feel free to grab another refreshment and mingle a little bit. And then I'll see you next time. Thank you so much.
Thank you.